for joining us for this second video in chapter 8, where we're starting to talk about what kind of reactions help us to prepare alcohol. Last time we talked about SN1 and SN2 reactions to make alcohols. That was hopefully mostly just a review for us, but here in this section of the chapter, we're going to start talking about redox reactions to make alcohols. Okay. And so we do need to review a little bit about redox. Hopefully you remember that well from Gen Chem. You might have been confused a bit because reduction means gaining of electrons and whatnot. But remember that I don't know how reduction and oxidation were defined for you in your general chemistry classes, but reduction really is about gaining of electrons, right? That's really what this word really means. And so maybe that's too much. Maybe not. Maybe I'll do this. So it's the gain of electrons is reduction, and then the loss of electrons is oxidation. Okay, and the word reduction really comes from the fact that, like, when you reduce a metal, in other words, give electrons to metal cations, they tend to become neutral, non-ionized metal, and then becomes precipitated as a solid metal from a solution of metal cations in a solution. And so in the old days when chemistry was developing, it looks like this metal cation that was in a solution reduced down to like a tiny bit of metal solid, and that's really where that comes from, if you were curious. But anyway, the reduction is gain of electrons, and for that reason if you gain hydrogen, which is very not electronegative, so hydrogen is very much willing to share electrons with you, and so it's, if you gain on hydrogen, it's almost as though you gained electrons. It's a similar idea with loss of oxygen, right? Oxygen is very electronegative, so when you have an electronegative atom attached to you, it's like as though you're losing electron density to the oxygen. But if you lose that oxygen, it's almost like you gained electrons. It's kind of like when I had back in my college days, I had a roommate who like ate my food a lot. When he moved out, the loss of Carl was like a gain of food, right? Similar idea. And likewise, so that same idea, you could apply that to like a more generic definition. So loss of more electronegative atoms, like oxygen, is a reduction, and gain of less electronegative atoms would be a reduction. And then of course we're comparing electronegativity to carbons, because remember, this is organic chemistry, we're talking about carbon compounds. So maybe I'll add that here. Okay, and then oxidation is the opposite, right? If you gain oxygen, which is very electronegative, it's gonna suck up your electron density, so that is loss of electrons. And hydrogen, which is willing to share electrons with you, if you lose that, it's like loss of electrons. So if you gain more electronegative atoms than carbon, atoms that are more electronegative than carbon, that's like losing electrons, so that's oxidation. And if you lose less electronegative atoms, that's reduction. Hope that makes sense. So here's one scenario. Methane, when it gets oxidized, which is often abbreviated like that, one oxidation state, then that is when you get an alcohol. Okay, and if this gets further oxidized, then carbon gains another bond to oxygen at the loss of a hydrogen, so you might get like an aldehyde. And then this, if it gets further oxidized, it gets another oxygen. It's like carboxylic acid stage, and if this gets further oxidized, you become carbon dioxide, and that's as oxidized as it gets. This is most. And then of course this is all the way reduced. There's not very many things that are less electronegative than carbon, so this is pretty much as reduced as it gets. Now, in the opposite direction, right, from carbon dioxide to carboxylic acid, that's a reduction. This symbol means reduction. And then down to aldehyde, to the alcohol, and then further reduced to the methane. Now, one of the things we want to be able to do when we look at redox reactions is to assign oxidation states, because then we know for sure what's going on in terms of redox. Is this some reactions may look like a redox reactions, like when you add a water across a double bond, it looks like you gained an OH group, but it's actually not oxidation. It could be confusing, and so the best way to know for sure whether a particular reaction is a redox reaction is to assign the oxidation state to see what's going on to the molecule. So if they, here's how you would calculate this. If the atom that carbon is attached to is less than carbon in electronegativity, right, then that's oxidation state of -1 addition. Okay. For instance, if you have a CH bond, this is a -1 in terms of oxidation state, because it's the opposite of oxidation. It's like gaining electrons when you gain something like hydrogen. And then another rule of thumb, if you have a carbon-carbon bond, this is a net 0 oxidation state, increase or decrease, because carbon atoms have exactly the same electronegativity with each other, and so they just equally share the electrons. It's not like loss of gain of electrons or loss of electrons. If carbon is attached to something more electronegative than carbon, then that's an oxidizing situation, so it's +1. An example might be carbon is bonded to chlorine, let's say, that's more electronegative, so this would add +1 to the oxidation state. So see if we could calculate, maybe pause the video and calculate the oxidation state of all of these guys. And if you do, you notice that this carbon would be -4. How do I know that? It's -1 for each of these 4, so that's oxidation state of -4. Let's think about this alcohol carbon. It's -3 for the 3 hydrogens, and yet it's +1 for the alcohol, and so for that reason this is going to be -2. Hope that math makes sense to you. -3 + 1. This aldehyde, it's -2 for the 2 hydrogens. Oxygen would be -1, but notice it's doubly bonded to carbon, so that counts twice. So it's -2 + 2, and this is gonna be oxidation state of 0. Okay, so this is the oxidation state. The next one up, it's -1 for the hydrogen, but the +3 for the 3 oxygen bonds, and so for that reason this is gonna be +2, and then this is gonna be +4. Okay, so hopefully you're getting the hang of this. So let's see if we could apply this oxidation state calculations to figure out a particular reaction as a redox or not. You could basically categorize all reactions in organic chemistry as either reduction reaction, oxidation reaction, or neither. And of course, there's a lot of types of reactions under that neither category, as you'll see, but that's the aim here, is for you to be able to categorize a reaction, say like this. and see if you can categorize that as either reduction, oxidation, or neither. Okay, that's something I want you to be able to do. And what you do is you look at all the atoms that are involved. The atoms that are not involved in the reaction, of course, doesn't change. Like, can you calculate the oxidation state of this carbon? That's attached to 2 carbons, which doesn't change the oxidation state. That's 0, right? That's what we said over here. But it is attached to 2 hydrogens, and so for that reason, this is going to be -2, and that carbon is not participating in the reaction. That doesn't change, but we notice this carbon is experiencing changes, and yes, for judging whether it's a redox reactions or not, you want to look at the oxidation states of just carbons of your molecules. Okay, and this carbon hopefully makes sense to you. It's +2, and this carbon is going to be +1 for the oxygen, but -1 for the hydrogen. Now this carbon is attached to a hydrogen now, so this is going to be 0. So the oxidation state decreased, right? What does that mean? That means it's a reduction. It went the opposite of reduction. So this is a reduction reaction. Okay, I hope that makes sense. Let's think about reaction like this. There's an alkene that becomes an alcohol. That's something we're going to study in a couple of chapters. Again, you want to think about the oxidation states of carbons that are experiencing change. So this carbon is changing. So is this had just 1 hydrogen, but now it has 2. So we want to look at all those carbons. Now, this first one, hope that makes sense, that this is going to have an oxidation state of -1, and so is this. This is a 0, and this is -2. So what's going on? We went from total of -2 to total of -2. So notice the oxidation state did not change, which means this, even though it looks like a redox reaction because you saw a gain of oxygen, overall, right, on balance, this is actually a neither reaction. It's not an oxidation reaction because you might say, well, how come it's gained an oxygen, but here you gained a hydrogen at the same time, and that's why. Okay, let's do another example for practice or to explain this idea. Let's say we went from similarly to alkene to this compound, which again we're going to study something like that very soon. Right, in this case the oxidation state is -1 as we looked at, and this is going to be 0, and this is going to be 0. So you notice the oxidation state total went from -2 to 0. So that's a gain of oxidation state number. So this is an oxidation reaction, because the oxidation state number went up. Okay. So I just want to note that halogens are pretty much always considered more electronegative. Even though when you look at the Linus-Pauling scale number for carbon and say like iodine, you might not think so, but for the purpose of redox reactions, well, I just want you to consider halogens, especially iodine, as always more electronegative than carbon. Okay. I might add that typically reaction like this is very difficult, this oxidation. these reactions have a very high activation energy, so normally requires enzymes. So we're not going to see that kind of reactions in this chapter, if you're curious. Now, here's a example of using reduction to make alcohol from either aldehyde that has a hydrogen on the carbonyl, or 2 carbons on a carbonyl. That's a ketone, right? Hold on. That's ketone. If you reduce this, you're going to get primary alcohol. If you reduce a ketone, on the other hand, you're going to get a secondary alcohol. And of course, this is secondary because the carbon that bears the alcohol is attached to 2 carbons, whereas this is attached to just 1 carbon. Okay, so how do you do that? The typical reagents that you need for this are sodium borohydride is one. Another one is lithium aluminum hydride, and there's some difference. Okay, so sodium. And this is lithium aluminum hydride. Okay. And if you look at the structure, it looks like this. And of course, the sodium is just a spectator ion, so we're not going to draw it or consider it. Same with the lithium here. Or you could consider it a spectator ion. So there's a negative charge in the central atom. And can you tell which one of these is more reactive? Well, boron is more electronegative than aluminum. Aluminum is less electronegative and yet has a negative charge, so that's very uncomfortable. So this is more reactive. Okay. And so for that reason, this is a very explosively reactive agent. And then if you introduce any air or especially moisture, this can react really violently, so it's really dangerous. Or if you have a very concentrated solution of this aluminum hydride can react very violently. And so for that reason, like, I typically get my palms sweaty when I write out lithium aluminum hydride. That's something you want to really be careful if you do use it. So for that reason, this can only be used in polar aprotic solvents only, and in fact pretty much only ethers. So diethyl ether, or THF. Okay. Of course, diethyl ether looks like that. Okay. If you use other things like DMSO or DMF, this is so, even though you might think those are polar aprotic solvents, this is so reactive, it can react with those. Okay. The sodium borohydride, on the other hand, it's not as reactive as this. It's a more sluggish reaction, but the benefit is you can use this in many different solvents, even in alcohol solvents. It won't react, even though it's got it's protic, right? So you do this with, that's abbreviation for ethanol. Okay. So that's some differences here. Here is an example of that. If you treat this ketone molecule with sodium borohydride and ethanol, you can get the corresponding alcohol. And what you want to think about is these species are good hydride sources. Okay. And you might think, why can't you use something like a sodium hydride, right? Well, hydride itself is not a good nucleophile. No. Hopefully you get that. Well, so these you can't use for the reduction reaction because hydride it by itself good nucleophile. You want the hydride to act as a nucleophile. And remember, this is not a good nucleophile because nucleophiles need to be polarizable. This is the least polarizable anion there is. It's the smallest nucleophile, and so that's the reason. Whereas these guys, the negative charge is distributed among these 5 atoms, and so for that reason, not through resonance, inductively, and so for that reason it's polarizable. That's why it can do a nucleophilic addition reaction. Okay, and so what does that mechanism look like? Well, the hydride or hydrogen takes these 2 electrons to attack the more partially positive carbon of the carbonyl, right? Because of the electronegativity difference. And the pi electrons would get kicked up to the oxygen. So you get that intermediate. And remember, if we're doing this in water, right, this alkoxide could pick up a proton from, I mean, in an alcohol, from the alcohol, because it's amphoteric, right? So you go through this alkoxide intermediate. Of course, this is reversible because the acidity of these 2 would be similar. So that's how you end up with the product. Now, and then the hydro BH4 minus becomes just borane. And this is not as reactive. And that's the end of the mechanism. It's not very long. Similarly, you could do this with lithium aluminum hydride as well in THF or something like that. The only difference is you have to follow this up with acidic workup, acidic aqueous workup, because there is no alcohol in this mixture or anything product, and so the alkoxide needs to be quenched by a proton, and that comes from the acidic aqueous workup. We often use that word a lot. Workup just means at the end of the reaction you just throw in some water, right? You don't want to do that at the beginning because water would react with aluminum hydride and explodes, and that's all that happens, and this would not react, right? So we often say aqueous workup is needed to quench the negative ion or something like that. In this case, it's just a proton source, okay, to get to the alcohol from the alkoxide, okay. So you should practice drawing the mechanism for this as well.